Okay, so the last second session is Luca Barbiero from the perspective of Torino. We'll tell us something about exploring spending.
Can you unmute your Zoom session?
Okay, good. So thanks again for the invitation. And of course, thank you so much for setting up this nice meeting in this fantastic place. So, okay, today I would like to show you that magnetic atoms, so in optical lattice, can be a quite powerful resource in order to explore state of matter where fermionic particles strongly interact. So as we know, so in these regimes, some of the most important and fascinating phases can emerge. So paradigmatic example is magnetism. No? So here, basically, we know that strong interaction can give rise to a breaking of the spin rotational symmetry and of a spin gap. So I would say that this phenomena is quite well understood. So what is instead much less understood is the phenomena of superconductivity, right? So here, we have some theories working in some specific cases, but I would say that we are quite far from, the end of the story. But here, what we know is that, for example, what we need to have in order to talk about superconductivity is the breaking of a U1 symmetry, okay? And this can also give rise to, this usually gives rise to a spin gap. But it is also very important to underline that we can talk about superconductivity in one-dimensional systems. So in this case, so superconductivity is associated to algebraic decay of superconducting correlation functions. And in particular, we can talk about superconductivity when these correlation functions are the leading order, as we are going to see in few slides. So another very fascinating state of matter that we can engineer thanks to strong interaction is, topological phases. So we already heard about that. So in particular, we know examples of topologically protected phases, specific spin liquids, fractional quantum Hall effects, toric codes, and so on. But it's also possible to define different kind of topological phases. So in particular, symmetry protected topological phases, like, for example, the case of the Haldane insulators that we all know. So here again, so what we need to have is the breaking of some symmetry. And in particular, most importantly, I would say we need to have no local order, okay? So captured by some no local order parameter, usually a string order parameter. And of course, we need in most of the cases a gap. Now, some of these states of matter are believed, I would say, to characterize the phase diagram of two-dimensional fermions. This is a sketch of the phase diagram of cuprates, okay? So two-dimensional electronic systems. And so as I said, in presence of strong interaction and as a function of temperature and doping. Now, as you can see, so there are no numbers, okay, in this axis. And okay, this is not because I'm lazy, okay, maybe I'm also a bit lazy, but the main reason is that, considering these setups in a very accurate way is very, very complicated. So we know that most of the solid state experiments are limited. So we have, imperfections, we are limited detection scheme. And even more frustrating for me that I do theory, so is the fact that most of the numerical approaches that we can use are limited. So we know that most of the QMC method, they have the sign problem. MPS approaches are very limited in size. So, it's problematic. But here is where I would say that cold atoms experiments, can really provide fundamental informations, okay? And this partially has been already proved. So we had the first realization of a fermionic Mott insulator more than 15 years ago. So recently, we also had realizations of antiferromagnetic phases. Nice. And also we had something more exotic, so related to the physics of bad metals. And it's also important to underline that in, quasi 1D or quasi 2D, depending on how you like to call a two-legs ladder. So we also had an experimental realization of an SPT insulator, okay? Now, as you can see, what is really missing, is, an experimental realization of superconductor in cold atoms experiments and of some SPT phase not being an insulator, like an SPT superconductor or an SPT liquid. Good. Now, what you can see that, in all these references that I'm showing you here, so there is a common ingredient, and the common ingredient is the model, okay? So you can see that there is Fermi-Hubbard model everywhere. So here, fermionic atoms in optical lattice is basically equivalent to, say, Fermi-Hubbard model. These are results in 2D. So we would like to see whether in 1D, in the one-dimensional Fermi-Hubbard model, where at least we have full control of the numerical method, so we can very efficiently use MPS, whether we can engineer some of these phases and and provide some new information. So this is the Hamiltonian that we all know. So the one-dimensional Fermi-Hubbard model. So U is the on-site interaction, T is the Hoping amplitude. We want to work in the strongly repulsive regime. So at half filling, this is the configuration that you should expect. So a Mott insulator. These colors just refer to the different spin orientations. So, but as we have seen, so some of the phases that I show you, so emerge in presence of finite doping. So basically, we have to remove particles, and if you do remove particles, the system is not anymore an insulator. So there is particle motion. And in this configuration, we can simplify quite a lot this Hamiltonian description. So in particular, what we can do is that so the interaction is so large that we can neglect double occupancy. So we can project this Hamiltonian into the subspace without double occupancy, indeed. And then since there is one parameter in this Hamiltonian, which is much larger than the other one, so we can perform perturbation theory. So up to the second order, and if you do so we get the very famous isotropic TJ model, where strong interaction actually gives rise to this effective isotropic spin-spin antiferromagnetic coupling. Now, basically, this Hamiltonian, this regime of strongly interaction has been reproduced in a series of papers in the group of Immanuel Bloch mainly, by using alkaline lithium atoms. Okay, so for this reason, let me call this TJ model alkaline TJ model. Okay, now let's see whether by using this model we can explore some of the state of matter that I showed you before. This is going to be quite straightforward, I would say. So first thing that we have to notice is that the spin interaction is completely isotropic. So there is the spin rotational symmetry is fulfilled, and as we know in 1D, we cannot break this symmetry spontaneously because of the Mermi-Wagner theorem. So we can exclude that we can reproduce any magnetic phase by considering this model. Then let's see about superconductivity. Okay, so we know that J is much weaker than T. As J goes like T squared over U, and in order to have spin-spin interaction, U has to be much larger than T. Okay, now this is the some theory results that has been obtained more than 10 years ago. So showing that in order to have superconductivity in this model, so J has to be larger than T, right? And this is not realistic, clearly, by using alkaline atoms. So we can also exclude to have superconductivity by considering this model. Now, I can also tell you that you cannot have any SPT phase, okay? So there is no chance. Of course, this is a still quite important model. So you can see in a series of papers by Fabian and Bloch and others to see that some interesting effect can really emerge. So, but let's try to fill a table, okay? So I would like to show the different setups that we can use. So basically, with alkaline atoms, as we said, the on-site interaction has to be very, very large. So the spin rotational symmetry is preserved, so no magnetism. The magnetic coupling is very weak, so no superconductivity. And the filling, the doping, if you want, is highly tunable. Okay, this is good. Now, in order to, overcome these limitations, so people in the cold atoms community started to think about different experimental platforms, And I would say the first very fundamental results has been proposed more than 10 years ago by Gorshkov, Manmana, and Anna Maria Rey and others. So here, basically, they propose to use polar molecules, as we heard yesterday in the Luis talk, into different row vibrational states. You can map these two row vibrational states as a spin up and down particles, and each of these two states has an induced dipolar momentum. So we know that polar molecules do interact via strong dipolar interaction, and this dipolar momentum can be tuned by playing with an applied electric field. Okay, now at the end of the day, so to make a long story quite short, so you can derive an effective TJ Hamiltonian, which is different with respect to the previous one. So, and the important thing, so there are three main things that you have to notice here. So first, J pair can be clearly different than JZ. So the SU2 symmetry is broken, okay, is explicitly broken. And this is a nice point. Second point, so Vij is long range, okay? So these couplings are not limited between nearest neighbor sites. And then the third very important ingredient is that the spin-spin interaction are completely independent on the on-site interaction. So these are huge difference with respect to the alkaline case. Good, but the thing is that, so with polar molecules, so polar molecules are quite complicated, to be engineered in optical lattice. So basically, we had the first proposal in 2011, and we had to wait till April 2024 to have the first results in this direction. These are the paper that Luis was referring yesterday, so by Junye. So here, basically, they have these polar molecules in a quite complex geometry. They can do some out of equilibrium, and they can also tune, these spin-spin couplings. So, but there are many problems, okay? So you can see that these spin-spin couplings are very, very strong. So which means that in order to have them to compete with the Hoping, so maybe we need a very shallow optical lattice. It is not so clear whether we can really work with the dimensionality, whether we can really achieve the ground state, or at least a temperature low enough. And even more problematic is the on-site contribute. So in the best case scenario with polar molecules, the on-site is hardcore. So you cannot have two molecules in the same site. In the worst case scenario, you have two body recombinations. So basically, because of chemical reactions, two molecules are destroyed and they become something different. Okay, but at least, so let's keep going with this table. Okay, with polar molecules, we know that the on-site interaction in the best case scenario is hardcore. So the spin rotational symmetry is broken. So we can have some magnetic phase, maybe. So the magnetic coupling, is very, very strong, maybe too strong. Let's see. But in principle, it's good enough to achieve superconductivity, while the filling is really tough to be tuned. So usually they can work uniquely at very low filling. Now, but there is another, experimental platform that, can be quite powerful in this direction. And as I said, so I'm talking about magnetic atoms. So yesterday, Elena gave a fantastic seminar on this setup. Now here I'm describing magnetic atoms in an optical lattice. Okay, so we want to trap these magnetic atoms in a 1D optical lattice. And in particular here, I'm considering erbium 177. So basically this kind of isotope is an effective 19-half spin model. So, but here, as you can see, so we have different ingredients. So in particular, we have the tunneling amplitude, we have the on-site interaction. So the on-site interaction is completely correlated with respect to the spin-spin couplings. And the on-site interaction basically is induced by two different contributes, okay? So the first one is the dipolar interaction, and the second one is the scattering, S-wave scattering length. And we know that, there are experimental results. So basically, they found flashback resonances. And in this way, we can basically achieve any value of U. So 0, positive, negative, whatever. Now, another important result that you can see is that, so it is possible to isolate these two states. So we don't want to work with an effective 19-half spin model. No, we'd like to work with an effective spin 1/2 model. And this is exactly what they did. Now, if you plug this plus and minus 1/2 in these terms here, so you can easily see that in this case, J perp is much larger than JZ. So basically, the Hamiltonian that you are considering is a TU-J perp model, which is nice because it means that the spin-spin interaction is strongly anisotropic. So the SU2 symmetry is strongly broken, I would say. Then, the most important thing is that also we need to have this spin-spin coupling strong enough. And this also can be done. So in particular, so there are papers by Francesca and by Marcus Greiner working with this, quite short optical lattice. And then if you do that, so basically you can calculate this J perp, which is, around this some Hertz. But most importantly, so we can also have the Hoping of 1 or 2 Hertz, so which can clearly strongly compete with this spin-spin interaction and also with the on-site repulsion. Good, so then we are ready to, to complete this table. So I hope that I convinced you that, okay, the on-site interaction is completely tunable. The spin rotational symmetry is broken. The magnetic coupling is strong enough. And the filling is, can be tuned quite easily. So I would say that this is the most versatile platform that you can have in order to explore TJ physics. Now, but let's see which kind of many body phases, we can achieve. Now, let me just define a couple of quantities. So it's going to be fast. So we are working away from half filling. Okay, so we cannot have a charge gap. So the only gap that we have to consider is the spin gap. So this one, basically the energy that the system can pay in order to flip one spin. And then it is important to define a couple of order parameters. So in particular, this is a string order parameter, which is usually a signature of symmetry protected topological order. And then a parity operator. So the parity operator is usually related to fermionic pairing. Now, we start by considering this one-dimensional magnetic atoms TJ model with attractive dipolar interaction and repulsive on-site interaction. So these are our MPS results. So you can see that as long as you switch on the dipolar interaction, indeed, so the spin gap is finite. And as well, so the parity operator is finite, while instead the string order parameter is always 0. So in this way, we can exclude the appearance of any topological phase. Now, since we are in 1D, we can use Lattinger theory. So in Lattinger theory tell us that this Kc, this quantity, which is related to the structure factor. So in particular, so once this Kc becomes larger than 1, so this is a clear signature of the fact that superconducting correlation functions become dominant, okay? So this is a signature of superconductivity if you want. But since, here we can use MPS, so we can also work away from this perturbative limit where Lattinger theory is supposed to work properly. And so let me just define correlation functions, the correlation functions that we need to consider. So the first two are related to superconductivity, in particular singlet and triplet superconductivity, while this charge density wave and spin density wave just show whether you have a charge or spin orderings, okay? Now, these are the first case that you are considering here. So in particular for this red area here, so trust me, it is not so clear, I know, but the leading order is a charge density wave, okay? So no superconductivity. But as long as we cross this line here, you can clearly see that the leading order is related to singlet superconductivity. And these are first nice results, I would say, because this means that, in a very friendly experimental regime, we can explore one-dimensional superconductivity by having magnetic atoms in a 1D optical lattice. Now, okay, this is what happens for attractive dipolar interaction. So let's see what is going on when we, change the orientation of the dipoles and we move towards the repulsive regime. Now, these are again our results. No? So again, spin gap. The spin gap now is 0 at the beginning. Then once we increase J perp, the spin gap becomes finite. And eventually it goes to 0 again. Now, importantly here, you can see that the fact that you have a finite spin gap is captured by a finite string order parameter. So finite string order parameter is a signature, as I said, of topological order. So in topological phases, we know that we need to have edge states. And indeed, so if you plot the edge magnetization, we have a finite edge magnetization exactly in this phase here. And in order to enforce our claim about topology, what we can also calculate is the entanglement spectrum. So the entanglement spectrum is nothing else the eigenvalues of the reduced density matrix. And here, theory tells us that if we get even degeneracy of this quantity, this is a strong signature of an SPT phase. And you can see indeed that this object here is clearly degenerate. So here we can really define a topological phase. Crucially, this topological phase is not an insulator. So contrary to all the insulators that have been realized in experiments, so these are, what we called an Haldane topological liquid. Okay, so in particular, you can see that in this region here, the leading order is a spin density wave. So that's why we call it like this. And also we have a normal Lattinger liquid and something a bit, strange, I would say, because this phase, this cyan phase is gapless, but the leading correlation functions is related to triplet superconductivity. This is quite strange. I wouldn't call it a superconductor, but still it's a strange Lattinger liquid. But what I want to underline is that, okay, here we can really engineer an SPT liquid conducting phase. Now I can show you the phase diagram that we have. You can see that the superconducting phase and the topological liquid, they are quite stable with respect to a quite large range of parameters, okay? But there is something very crucial to be underlined. Now, suppose that we set the on-site interaction equal to infinite, okay? As in the case of polar molecules. So you can see that this topological liquid completely disappears. So there is not any topological liquid with U equal to infinite. So this basically proves that magnetic atoms are, at the moment, I would say, the unique, resource in order to engineer this conducting topological phase in 1D, clearly. Then I can also show you that these topological and superconducting phases are quite stable with respect to density. So this means that experimentalists do not have to fight with any fine-tuning of the particles number. So, and these also are quite nice results, I would say. Now, finally, I would like to show you our recent results on a different regime. In particular, until now, so we have set the on-site interaction to repulsive values, and we did change the orientation of the dipoles, okay? Now here, since, as I said, magnetic atoms are quite versatile, so we can also explore the regime where the on-site interaction is attractive, okay? Where U is negative, slightly negative, of course. So, and these are preliminary results, so I apologize if you don't have many points here, but I think it's quite fair to say that we have phase transition. So, as you can say here, the spin gap is finite, then it goes to 0, it becomes finite again, and eventually it goes to 0, right? Now, this red phase here is characterized by a finite parity operator, while in analogy with the previous case, this yellow area here is characterized by a finite string order parameter. And again, so we can easily say that this phase is topological because we have a finite edge magnetization and even the generator rectangle in the spectrum, right? But what is really important now is to explore the behavior of correlation functions, okay? So this red phase here is again characterized by leading singlet superconductivity. So it's completely analogous to the previous case. But now you can see that the leading order in this SPT phase is a triple superconductor. So which means that superconductivity in this regime strongly coexists with topological order. And this clearly is an example of a topological superconductor in 1D. So probably completely different with respect to the topological superconductivity that you would expect, for example, in the one-dimensional Kitaev model, but still something I would say quite new. And certainly, so implementing this model is much easier than trying to implement any Kitaev model in 1D. So I would say that these are quite stable platform to study, one-dimensional topological superconductivity, which has never been realized in any cold atoms experiments. So, and with this, I think I have to conclude. So in particular, I hope that I convince you that, magnetic atoms in optical lattice can be a quite powerful resource, okay? So if you want to understand better topological superconducting phases or even normal superconducting phases, so these are the things that we are trying to understand now. So we know that in Kitaev topological superconductors, so we have Majorana fermions. What do we have here? I don't know. I don't know if we will ever know something about that, but we are trying. Of course, we would like to increase the dimensionality of the system. And finally, so we know that we can use this setup, these TJ models also to explore lattice gate theories. So in particular, the dynamics of mesons. And with this, let me just introduce the people involved in this project. So all the simulations have been performed by Leonardo, who is a PhD student doing theory in the Francesca's group. And we had, fantastic discussions with the Erbium team, in particular Luis and Ferdinand, and of course Manfred, Francesca, and Tom. And with this, I conclude, and I thank you for your attention. Yes.
The base of the universe will always come from Cooper, that tunneling from a higher dimension to lower. Basically, what do you mean by saying that everyone's? That's what I said. Yeah, absolutely. So then Latin that everyone can find or similar to the first. So when the relation that you find all the possible relation functions. We have the correlation function captured this superconducting order is the one going to zero much slower with respect to all the other ones. Saying you have exactly. I thought I longer important the correlation functions because not the environment. Okay. Did you go back to one slide where you mentioned that you found that you get
Yes.
There was something that I couldn't quite understand.
The topological superconductor. Yeah. No, no.
But then,
No, but there is a misunderstanding. Okay, so the PJ mode, so you have oops. So you can PJ mode you, but the constant interaction is very large, basically, right? So the magnetic atom, so the speed interaction is not induced by constant interaction, it's induced by bipolar interaction. So this the fact that the speed interaction is completely correlated with the constant line.
okay, so you simply have, by the way, yeah, so we have a long range J. So the J is long range. And
Taker, it's all taker.
and then just taking about time exploring and statement about sharp fluctuations that you use in order to energetically give parameters.
Exactly. Hi, so I have a question. What is exactly the characteristic of this? Like, how do you define the ability of this one ability of the other? And there's this paper by Angus Sigmund and Ed about the Steinberg model, where they show that cosine is time. You're stating what it was. Okay, I did not have time to go to show side better time. So basically, you can take this isotropic PJ model for visualizations and end up with a sine product model. Okay. Now, what's really important is the Binning field of your cosine curve. Now, so what you see that the Binning field, depending on your rotation, is equal to square root of pi over 8. Yeah. So basically, you assume that you have finite figure parameter. So totally accumulated without the phase if you want. Same way. So you can have like eventually of like the edge, like how do you get?
To clarify what something in the sense that you involve only back a couple of lines.
Yes.
Then we have long range interactions.
Yeah, but that's not okay. It depends how you define long range interaction. So it might be formally similar to a long range interaction with the K for example, an error not part of more than one, but we should do this long range. One over two is short range one, right? So that sheet the base power is okay.
Okay, so I think the one before you. Luca.
Yeah.